Let's today talk about different types of parameter adaptation algorithms that will be useful for implementation in practice. We started from last time the concept of parallel adaptation with the regressive vector containing the estimated signals output instead of the true outputs. And our observation is that that can potentially be beneficial for performance in noisy environment. And that little change actually resulted in one change in the feedback block diagram construction here. The new change is we have a filtering of the adaptation error epsilon, a posteriori adaptation error epsilon, instead of the simple form where this linear block is just 1. In this case, epsilon k plus 1 is 1 over a q inverse, filtering through this theta transpose times phi signal. And then this is exactly the same. Right? So that means this feedback version, this nonlinear block, last time we spent time to construct how it looks like element-wise. This time I won't spend the time to draw all the details of this block diagram. But this feedback block with epsilon as the input and going through this operation over here, this is the same as before. So that means we have the good news. This is going to be passive. Because it's the same feedback block. So therefore, it is very quick to derive the stability condition for this parallel PAA algorithm. Hyperstability conditions are first of all, the LTI block, which is this, is SPR. And then second, the nonlinear block, it is already passive. So it satisfies the Popov inequality. This is assured. And more specifically, actually, we can know from previous analysis for this block, we have the result that this Popov inequality will be lower bounded by something related to the initial condition. If this is a constant adaptation gain, right? So the second condition is satisfied, and the requirement is this one. If these two conditions are valid, then we have asymptotic hyperstability. So that's a very strong condition. Let's think about this a little bit. Let's think about these two conditions a little bit. The first one, in your homework, in your recent homework, you did an exercise. For transfer function that look like this, it is going to be guaranteed to be STPR under certain conditions, right? So this is guaranteed. homework, the write-up is as follows. This is SPR if all the coefficients n of them. If the summation of all the coefficients, the absolute value of them, is less than 1, then this is guaranteed to be SPR. And this is also stable, as you have proven in your homework. In general, if you are given just a stable transfer function, if all the poles of this transfer function are inside the unit circle, it's not guaranteed to be SPR, though. Only this very special case it is. So in general, however, use G. So in general, this is not guaranteed by stability unknown. So that gives us some motivation. We'll need relaxations. We'll need design to relax the SPR requirement. So it turns out we can construct this. We can add a few more things into the PAA so that this LTI block will be something different, not just with the A in the denominator. Then we can make the SPR condition to be a little bit easier to satisfy. That's the first thing that we will cover today. Second is this piece over here. If we go to here, we know that this is passive for constant adaptation gain. For time-varying adaptation gain, we have a remaining assignment to prove stability, hyperstability in this case. So that is doable too. That will be the second piece of assignments for us, if not today, by next week. So let us do the relaxation of the SPR condition first. We're going to do two cases. We're going to do the constant adaptation case and then the time-varying adaptation case. For the constant adaptation, let's think about why this appears here, why this looks like that in the LTI block, and how we can modify things a little bit. It is here because this left-hand side, we have the adaptation arrow needs to go through this filtering process. And this adaptation arrow is directly utilized as the input to this nonlinear block. So if we can do filtering on this side, can we do some filtering? Can we create something such that we have a numerator appearing somehow in this process? So in other words, this filtering is, we introduce some additional filtering in these two equations. And the approach is as follows. Do instead, so case one, we're going to introduce a new type of error signal. That is a filtered version of the original adaptation error, a posteriori adaptation error. And we're going to use this new filtered version to drive the adaptation gain, to drive the adaptation formula. Everything else remains the same. And if this is the scenario, then we will expect, we know this remains to be true. So for nu, this is nu is a filtered version of epsilon. Let's think about how nu will depend on theta, tilde, and phi, these important vectors. Nu is C operating on epsilon. So we will have, this is C negative theta transpose phi k. Right? And then if you put this into block diagram, we are going to have the theta tilde transpose phi going inside here again. And then it's going to go through first the negative sign, and then it goes through this filtering. To generate nu. And nu drives this adaptation error equation. So theta hat follows this. Theta tilde is going to follow exactly the same structure, right? So theta tilde formula, the nonlinear block is going to be exactly the same. Then, in this case, we have successfully introduced some new terms in the linear block. So if Fk, this is our assumption, we work on the constant adaptation gain case first. If it's a constant adaptation and the C over A, this LTI block is SPR, then we're going to have assured stability, hyperstability. So that's the concept here. This, if you think about it, what would be an ideal C filter in here? That will exactly give us SPR condition quickly. So if somehow I know about the model that I try to identify, I know where the denominator is, then I can create a filtering process such that these two will give me one guaranteed SPR condition. Now, that may not be easy though, so it's not very quickly to guess something out of this. It is possible to find an optimal C if you have some knowledge of A. That is one approach to do. If you don't have any idea, you cannot do any prior estimate of this A, then there is another approach that we can relax this. The other approach is I'm going to somehow make this filtering process to be adaptive as well. So I'm going to change the C on the fly. And ideally, if I do it correctly, C will converge to A, and then we're going to have SPR assured condition. So that's the concept. In details, that's an approach. So this is called a parallel algorithm with a fixed compensator. So we can also do parallel algorithm with a adaptive compensator or adjustable compensator. So let's take a look how that will work. The algorithm is as follows. If we know if A has this structure that we usually assume, we know it's nth order. We don't know anything about these coefficients A1 to AN. Let's do an adjustable compensator. I change all the coefficients in this adjustable compensator, and I do nu to be this filtered process. At every time instance. So this is the a posteriori signal again. The a priori signal is to use information up to epsilon, up to k. So use everything. Use the a prior signal of the estimation error, adaptation error. Let me write it slightly more carefully. So nu k is c hat epsilon. So that's epsilon k plus 1 plus c1 hat k plus 1 epsilon k plus all the way to cn hat epsilon k plus 1 minus n. All right, so that's the filtering step. This is not implementable at time k plus 1 because this is not available at time k plus 1. This is a posteriori. This is available at time k plus 1. So the concept of the a priori adaptation error is to use whatever that I can have available at time k plus 1. So I'm going to use the a priori version of epsilon, and then I use epsilon k because at time k plus 1 I can immediately have this. So that's the subtle difference between this kind of filtering with the previous one. Then c hat n k plus 1 epsilon k plus 1 minus n. So that's the a priori filtered adaptation error. This is going to drive the adaptation algorithm as follows. So let's say the adaptation vector is theta. I put a e to indicate this is extended version. It's going to be driven by, let's do the implementation version. All right, so I put subscript e as much as possible to indicate this is different. The construction is different. The structure is the same, but the signals will be different here. More specific, let's think about under this scenario how we should choose the regressor and our adaptation vector. In this scenario, both A and B, A and whatever appears in the, let's say, the plant whatever appears in the coefficients A and B, they should be included in theta. But we should do something else, slightly more carefully in this case. Because C is also changing, right? So this is also something that's changing at every time instance. And we need to have a way to update them. So this theta E actually contains not just A and B, but it should also contain C vector. So C1 hat all the way to Cn hat. That's the first difference. And then second is this regressor vector, phi, is also going to be having more terms inside. Just based on first observation, the dimension. If theta dimension is increased by n, then you need to have phi e to have the same dimension. So phi e we should add another n elements to the regressor vector. Previously, we had negative yk hat. This is written earlier. And then uk, etc. In here, we need to somehow incorporate look at this regressor adaptation arrow nu over here. In here, it turns out we need to include, let's see, C1 is multiplying with epsilon k, and Cn is multiplied with epsilon k plus 1 minus n. So it turns out we need to add these elements in here. The structure that these additions follow from here. So C is, we have n C hat that appear because we have A1 to AN over here. In the regressor vector, this appears because we have yk plus 1 equal to negative A1 yk minus A2 yk minus 1, etc. So the corresponding regressor vector is the data that is appearing at the same location as AI, the variables. And then similarly, the regressor vector elements that you need to add here, they come from the structure where Ci hat gets multiplied with a data element. C1 hat gets multiplied with epsilon k. Cn hat gets multiplied with epsilon k plus 1 minus n. So they are added in here. And then the F vector, F matrix, this is also in a different dimension. So they should be updated by, I'm going to use the inverse formula. If I have a forgetting factor, it should be like this. It should add, at every time instance, this new regressor vector times its transpose. So that is this filter, adjustable compensator version And as it turns out, so this has the PAA. The important thing is, if you do it this way, PAA has let's do it this way. The linear block is going to be SPR guaranteed. So this is the overall picture of all the potential PAAs that we can implement. And the logic is on relaxing this SPR condition. All right. Let's write the LTI block as a general transfer operator. If so, H, this LTI block can have different forms. It can be 1, it can be 1 over A, it can also be C over A. And the different PAAs that corresponds to this LTI blocks, different options are H is 1 if it's series parallel our first PAA, recursive least squares, or it can be parallel with an adjustable compensator. If H is 1 over A, then this is PAA, this is parallel PAA. Okay, without any compensator. And then this one is parallel with fixed compensator. We have what we have covered so far is the stability condition if the adaptation gain is a constant. This is our case 1. So I will state the general case for time-varying adaptation gain now, and then we're going to work out the specifics. The general stability conditions are if, I'm going to write out it more carefully, if is constant adaptation gain, then H being SPR will give asymptotic hyperstability. In the general case, with some forgetting factor lambda 1 and lambda 2, i.e. the formula on the right-hand side of the whiteboard, this most general case, then the stability requirements is that there is slightly an extra term that is appearing that makes this new. This is still LTI. This is still linear time invariant. In this case, we need this one to be SPR. Well, this lambda is the maximum of lambda 2. This is the general stability conditions as an overview. We won't have enough time to cover this part, so let's work on this next time.